All right. Hey, folks. My name is Andrew Seigner. I work on Linkerd. We're going to go through a little bit of background on Linkerd. Then we're going to turn it over to Frederic to go through Thanos. And then hopefully we're going to do a demo that works, that integrates the two, and kind of shows kind of the benefits of these two projects working together. So just a little bit of background. Linkerd is a service mesh. A service mesh really does three things for you. It gives you observability, security, and reliability across all of your applications, and you shouldn't have to change any of your application code. It's usually composed of two major components: a control plane, which is kind of the administrative side of it, where you do things like observability, like you roll up all your metrics, you can set policy on managing traffic, and it's like your user interface into it. So you have a CLI or like a web dashboard or something to interact with it. And then on the other side, you have the data plane. The way we can enable all of this stuff is we put a little sidecar proxy next to all of your applications. We inject a little proxy into each pod. So the origins of Linkerd actually go back almost 10 years. The company I work for, Buoyant, is composed mostly of former Twitter engineers. The libraries that Linkerd 1 was built around were built at Twitter when we were decomposing the largest Rails app on the planet into a bunch of microservices. And there was this need for this uniform observability, reliability, and security. And that was kind of the motivation for, that's why Linkerd 1 ended up being written in Scala, which worked great for a while, but in a world of like, everybody's running a little Go process, and you're taking up 5 or 10 megabytes of memory. Trying to run a JVM as a sidecar that may need 100 megabytes or a gigabyte of memory, it didn't really fit. So about a year and a half ago, we set about doing a complete from the ground up rewrite. We kind of looked at like what we had learned over the last several years with Linkerd 1 and made some like pretty specific design decisions with Linkerd 2. The first one was it would support Kubernetes only. Linkerd 1 would run anywhere, and we will continue supporting it for a long time, but it made configuration pretty complex. It could use Zookeeper, it could use Mesos, whatever. By just targeting Kubernetes, it's super easy to set up, and you'll see that in a demo in a little bit. The other piece was that Prometheus was gaining a lot of traction, and we had most of our users were wanting integrations with it. And we had some reference designs on how those two things would work together with Linkerd 1. But in Linkerd 2, we decided to just make Prometheus like a first-class component of Linkerd 2. So when you install Linkerd, you get Prometheus with it. The other part was looking at kind of the available languages. Go seemed like a very natural fit for the control plane. We're integrating with Kubernetes, so we end up using a ton of libraries that are in the Kubernetes codebase and related projects. It's been really helpful to like use that code instead of writing our own. For the proxy, we knew we needed performance, and so we kind of took a look at what was out there, and Rust seemed to fit the bill. We've been lucky enough to work with a number of the Rust community, like library developers, the folks that are responsible for things like protocol and I/O, and they've helped out a lot in helping build up this proxy. So just kind of a really quick picture of the architecture. If you remember that two components of a service mesh, you've got a control plane and a data plane. I'm not expecting you all to understand every box here, but these slides are attached to the schedule, so you can dig into it later and come ask me questions. But really, I just wanted to call out, like, there is an observability layer in here, and that's what we're really focused on for this talk. And we're using Prometheus. Like, we found it's worked so much better than trying to invent our own. And in the spirit of reusing things, like, we just plug a Grafana right on top of it. And so if you're using Linkerd, all of your observability tooling should work it should feel very natural, because you'll just plug in to the existing components. The way you interact with the service mesh, again, is through a CLI and a dashboard, and those are things that we provide to you. So just really quick, I wanted to focus on like kind of the core piece of technology that ties all of this together, which is when we inject that little Rust proxy into each of your pods, we're exporting some very specific metrics that give us kind of 3 golden things to look at. Request rate, success rate, and latency. And the demo we're going to do in a minute is going to focus mostly on latency, but by counting those things, it allows us to give you very useful metrics on how your microservices are behaving. So with that, Frederic.
Okay, so let's do a little poll. How many people here are already using Prometheus? Wow, that's almost everybody, so I'm going to run through this one a little bit more quickly. So, but there were a couple hands that didn't go up, so let's make sure everybody's on the same page. So Prometheus is a pull-based monitoring system. What that means is that Prometheus, in a regular interval, will go to our applications to literally an HTTP endpoint and grab all the metrics and ingest it into its time series database. So basically, the example that we have up here is we have our application, our user-facing application that is exposing Prometheus-style metrics, and Prometheus grabs those at one point in time and inserts it into the time series database. Then we actually get user-facing, our users actually are using our applications, we are actually making money or something, and these requests increase. And over time, the interval has passed, so Prometheus will come again and do a second request and insert that into its time series database. And this will just happen all the time and forever. And as I've seen, a lot of you already use Prometheus, maybe even on Kubernetes. How many use Prometheus on Kubernetes already? Great. That's also a lot of hands. Not quite as much, but also a lot of hands. So Prometheus, the Prometheus ecosystem has primarily revolved around within a single Kubernetes cluster. And everybody's here to see multi-cluster monitoring, obviously. But that part, I feel like we figured out pretty well. There are setups that give you out-of-the-box cluster monitoring. I happen to work on one of those. Prometheus has a lot of guides out there. There are lots of blog posts how to do app monitoring with all of these things. So I feel like we've covered this pretty well. But once people are comfortable with that, we have pretty much the same repeating questions. So what about long-term storage? How can I get a global view of all my clusters out there? Maybe even if I want to do some analysis over a year worth of data, my queries are getting really slow. So how can we solve this? And just about a year and a half ago, maybe a year ago, a team, actually 2 individuals at Improbable came up with a really, really awesome solution to this, and they named it Thanos. So Thanos does have all of these features, and you can kind of think of it as a distributed Prometheus. Basically, Thanos goes and takes all of these pieces that are in the, let's call it, monolithic application that makes up Prometheus, and it pulls out the query layer, it pulls out the storage kind of, and makes it a distributed Prometheus instead of the monolithic process. Now, that doesn't mean that you won't need your Prometheus anymore. We want to monitor our distributed monitoring system with a non-distributed monitoring system. But nevertheless, this is still a really, really awesome project. So I happen to be now one of the maintainers of Thanos as well, even though I do not think I deserve that. But the group was kind enough to grant me maintainership. So let's dive a little bit into more how Thanos works. So as you see, on the slide, we actually, even when we are using Thanos, we are still using vanilla upstream Prometheus. But how does that tie into the whole story? So the way Thanos works is that it gives us a sidecar that runs next to our Prometheus server, and that way basically puts a common interface in front of Prometheus that is the Thanos Store API. And I'll keep coming back to this Store API theme because I think this is a really cool aspect of Thanos. Basically, all the components within the Thanos project implement this API, and it's kind of the data exchange API for metrics, you could say, for time series data. So what the sidecar then does is Prometheus builds these immutable blocks of data. Prometheus always appends to the write-ahead log very frequently. That's when it collects data and writes to disk. And every 2 hours, it takes all of that and puts it into an immutable block on disk. So it's never going to be changed again. It's not entirely true, but let's treat it as that for now. And Thanos goes ahead and sees that, oh, there's a new immutable block. I'm going to upload that to object storage. And then there's another component called Thanos Store. I know, Store API, Store, not great naming, unfortunately. It's hard to change that naming now. But the Store API is essentially puts the story, sorry, I did the mistake myself. The Store component exposes the Store API as a wrapper around an object storage, like Amazon S3, for example. And that way, the Thanos Courier can read all the live data, basically, from the Prometheus that is live appending data, and the historic data from object storage. And that way, we can essentially, this is how the long-term storage part was solved, because we can treat object storage essentially as an endless bucket of storage. Now, Thanos actually, and this is how I got involved into Thanos, Thanos is about deployment flexibility. And while the sidecar approach is a really desirable one and it works extremely well, there are lots of deployment scenarios where you may not be able to have direct access to your edge Prometheus, where your Thanos Courier cannot directly do these gRPC calls to the Prometheus, to the live Prometheus instance. So actually, I had just had a conversation about Prometheus servers that may be running on cars, for example, or just things that may have interrupted internet connections. So in those kind of scenarios, it would be really nice if we can just have the Prometheus and stream all of its data over time. And if there's a downtime of our backend, then it would just stop and continue once it has an internet connection again. And for our use case, we actually are building this. I work at Red Hat. I work at sort of within the OpenShift organization. We're building this to monitor rollouts of clusters for automatic upgrades. And for that, we don't necessarily have access to customer clusters. We can't make random HTTP calls into customer clusters, obviously. So basically what we're making use of here is a feature that is already available in Prometheus called Remote Write. And what this essentially does is it replicates the Prometheus database that is local to the Prometheus server to a remote location. And the Thanos Receive component receives this and essentially replicates the database locally and then does the same thing as the Thanos sidecar does once the block has been produced. But the Thanos Receive component would run on our premise in that sense. So I want to reiterate on this. Thanos is really a toolkit of components, and you can use all of these components to build basically your own, very own monitoring system. So we're all here for multi-cluster monitoring. So does Thanos equal multi-cluster monitoring? No. But you can make it your multi-cluster monitoring system. And again, the Store API is I think this is the coolest thing about Thanos, because the Store API allows you to build all of these wild combinations of components that ultimately make up the system that you exactly need. So let's look at this and look closely. The slide that I had before, and I removed everything that does not have a Store API. And did you notice which component is still up there that you may not have thought? It's the Courier. So the Courier itself also implements the Store API. So what we can do now is we can stack Thanos clusters on top of each other. So we could even run a Thanos cluster in each of our Kubernetes clusters, and there still have long-term storage, horizontal scaling of the Courier, and all of those great things that we want to have when there maybe we have some network partition, so we can't call into these clusters at a certain point in time, but we can still fall down into the cluster and troubleshoot our problems locally there. So I think this is really what I want people to go away with here. Thanos is about flexibility, and you should architect your setup to your need. And the Store API is really the thing that allows us to do this with Thanos. So architect to your need. So with that, Ziggy's going to show us some action.
We'll see. All right, thanks a lot. All right, so let's get into a demo. Everything I'm going to show you is on a GitHub repo. So if you want to check it out, go to bit.ly, Thanos Linkerd, follow it now or follow it later or whatever. I want to call out, like, I didn't write a single line of code to do this. I definitely wrote some YAML. But kind of the goal of this demo is to show what you can do with kind of off-the-shelf parts that exist today. So to just kind of set the stage on what we're going to be deploying, we've just got a very dumb client-server sample application. And the client puts a bunch of load, by default, like 100 requests per second onto a server application. We're going to inject Linkerd into that. That's going to enable us to get our observability across like these applications that we're deploying. Then we're going to take that setup, just a simple client server in Linkerd, and we're going to deploy it across 4 different cloud providers: Amazon, DigitalOcean, Microsoft, and Google. And then we're going to roll all of that up into a Thanos query, and we're going to be able to view these metrics in an aggregated way. And then we'll use Grafana to kind of visualize all that data. To dig into specifically how the auto-scaling is going to work, I'll kind of walk through this really quick. So again, we've got our client server. We've got our Linkerd injected. Because Linkerd is working with Prometheus, we're getting things like request and latency information. Then the custom part of this demo is that we're going to attach a Thanos to the Linkerd that comes with, attach a Thanos to the Prometheus that comes with Linkerd. When you install like a vanilla Linkerd, obviously you don't get Thanos today, but the demo and the examples that I've got on GitHub kind of demonstrate how you could do this. And I found this other nice piece of software called the K8s Prometheus adapter. What that does is it takes Prometheus data, and in this case it's a Thanos, but because Thanos and Prometheus look exactly the same from an API perspective, I just plug it into the global Thanos query. And that allows Kubernetes to see this Thanos data as Kubernetes metrics. And from there, when a latency value goes above what we want it to, in this case 10 milliseconds, it's going to scale up the server replicas on all of the clusters. So kind of the gist of this is given running the same system across 4 different cloud providers, if there's a problem or an observability event in one of them, we can react and adjust in a bunch of other data centers. And to just kind of call out the line I've drawn around all of this, that's what we're deploying 4 copies of. The global Thanos query runs in one of the cloud providers, but we don't really care which one. It's just know that there's one of those and there's 4 of everything else. All right, let's see if this works. So the first thing I'm going to do is just show you some empty dashboards. I've already deployed the Thanos query because I didn't want to bother waiting for all of us to stare at this thing and deploy. But the important thing to note here is that we've got our Thanos query. It's configured to talk to basically 8 backends. There's 2 backends per cloud provider. It's those Thanos sidecar and Thanos stores that Frederic was talking about. The sidecar gives you like real-time data, and the store gives you like long-term data. Because Thanos can leverage object storage on each of these providers, whether it's like DigitalOcean or Google or whatever, it can plug into the appropriate object storage for that. So, okay, so each pane is a cloud provider, and we can confirm that just by, all I've done is set a special environment variable on each one. So I've got AKS, DigitalOcean, Amazon, and Google here. So I'm going to install Linkerd, and then I'm going to install the sample app. So let me unpack the command that I just ran there. So let's see. When you install Linkerd, like what I want you to take away from this is how easy it is to do that. We have a CLI tool called Linkerd. It's got, if you've used kubectl, it feels like very, very familiar. We use a lot of the same code as kubectl. If you want to install it, all you do is you type Linkerd install, and that just dumps a bunch of YAML. We tried to be really explicit about what we're doing, so if you're comfortable with that, you would just pipe it into kubectl apply. And I'm not going to do that now because I don't want to install Linkerd on my laptop. But that's like the entire installation procedure. You may have noticed that the command I just ran referenced an environment variable, which was a file. It's because I had to make a slight modification to the vanilla Linkerd to enable it for Thanos. But again, all of that's documented in the repo. So I'm just going to run a command really quick, a version check, just to make sure that all the clusters came up. It looks pretty good. I'm going to run one more command, which is kind of a diagnostics check, just to make sure things are looking good. Let me unpack this command a little bit. So we have, I'm just going to run this command against one of the clusters arbitrarily. Anytime you install Linkerd, you can run this check command. It runs a whole bunch of diagnostics and just make sure that like everything's up and running. I got a warning. It's okay. We released a new version a couple of days ago, and it's telling me I need to go update. But for the demo, I think we'll be all right. So far so good. The next thing I'm going to do is deploy our sample application. And again, I don't expect you to be like reading every line here. The point is that like this is like really simple and easy to get going. So let me unpack the command I just ran there. So what I did was I catted a very simple client-server application. There's a client, there's a server, and there's a horizontal pod autoscaler with it that's configured to say our target value is 10 milliseconds. If our latency goes above 10, if our P99 latency goes above 10 milliseconds, start scaling up the servers. And the command that I was doing specifically was I was taking that YAML and I was piping it into a Linkerd inject command. That, one second, connected to a cluster. Live demos, full of anxiety, it's great. So what that inject command does, it makes one small change to your YAML. It adds an annotation that says when this thing gets deployed onto the cluster, please inject that Rust proxy into each pod. You can set this annotation at the pod spec level, at the namespace level. By default, obviously, we don't want to start injecting all of your applications, so you can kind of roll it out gradually. So if that all worked, I should be able to refresh this. Yes, we're almost there. So we can see that the global Thanos query is now connecting to 4 sidecars and 4 store APIs. So that means that all of the Linkerds have come up. We're now collecting metrics from each of those providers. If I flip over to this dashboard, I should start to see metrics. Things are looking good. So the dashboard we're looking at here, this is what you get like with a generic like vanilla Linkerd installation. The difference is that this dashboard is pointed at a Thanos instead of a Prometheus that's embedded inside Linkerd. That's one of my favorite things about this project, Thanos, because like all of your tooling, if it already works with Prometheus, it's going to work with Thanos. It's pretty awesome. So you can see that like what Linkerd is providing is those like golden metrics, that like success rate, request volume, and latency. And the P99 latency is the one we're going to be focused on for the autoscaling. So the one thing I did do, all of these dashboards you see here are what you would get by default by deploying Linkerd, but I added one for this demo, and it's specifically to kind of get a view on this particular application and what's going on. So if you look on the left, we've got one server instance like per cluster, and like those are the different providers. Each one is doing 100 requests per second, so we've got about 400 total. And then that's the gauge in the upper right is our global P99 latency. And that's aggregated across all 4 cloud providers. And that's the number that the autoscalers are going to be looking at as they scale up. So what I'm going to do now is I'm going to increase load on one of the cloud providers from 100 requests per second to like 2,000. And hopefully, if this all works, we're going to see the latency spike really quick, and then we're going to see the autoscalers kick in, and those things start to scale up, and that value should hopefully go back down to 10 milliseconds. So I'm going to set the replica count on my load generator on just one of the cloud providers on Google, just arbitrarily, I'm going to increase it from 1 to 20. So that's where we're going to get the 2,000 requests per second. This is all going to go pretty fast, so I'll try to talk through all the changes, but I think you'll get the gist. Okay, so we scaled it up. So the first thing we should notice probably, if this worked, is the middle column should start to have a huge request volume spike. There we go. And then all of a sudden you see the P99 latency value went from 3 milliseconds to 62. So like we're in trouble. That was a massive increase in P99 latency. Starting to come back down to 27, we should hopefully start to see the horizontal pod autoscalers kicking in if we did all of this right. Let's see. There we go. So Google was first to notice it. They should all start kind of scaling up. It's a little bit bumpy on the way up as new servers come online. Since we're looking at P99, it only takes one request out of 100 to like really like spike the metric. And as the server comes online, it needs to like do that first request and establish connections. It is a little bit bumpy as you're cranking up the servers. But you can see that we are starting to get these up. These have a limit of 10. But as those go up, I would expect that latency value to stabilize a bit. So we'll just give it like a few more seconds. It's a little bumpy. We're at 37 milliseconds. Hopefully it'll get down to about 10 milliseconds within a few moments. But you can see like all of this happened within a few seconds. And kind of the gist of this is that like you should not have gotten woken up in the middle of the night for like a 20x increase in traffic and a massive latency spike. And it's important to note that like, you know, typically horizontal pod autoscalers, out of the box, they work more often on things like CPU and memory, which are important metrics to look at, and they are valid things to scale on. But as far as focusing on your user's experience, whether it's somebody looking at a web page or somebody calling your service, something like a P99 latency value can be much more valuable to ensure that you provide like a consistent experience for the person calling your service. A couple more things I want to call out. So not only are we leveraging Thanos to do this multi-cluster setup, but because we're using those object stores, I've been working on this demo for a few days, and we should be able to go back way beyond what Prometheus would typically give you. Like default, I think it's like 6 hours or 24 hours or something like that. It's limited, right? But Thanos, because it's plugged into these object storage in each of the providers, we can go back like several days and kind of roll up all of these aggregated metrics over a long period of time. So really, the takeaways from this is that like all of this stuff just like should work like out of the box. You get P99 latency values with very little work just by installing Linkerd, and by installing Thanos, you get really nice flexible monitoring that can work across clusters if you want it. And yeah, it just kind of all works. I'm really upset that it didn't get below 10 milliseconds while we're standing here, so I might click back after a slide or two, but we'll see what happens. So let me just summarize really quick. Please check out both of these projects. As far as Linkerd, we've got a pretty active Slack channel. There's about 3,000 of us in there. A lot of me and my coworkers sit in there, so please come say hi, and thanks a lot.
Okay, I guess we'll leave that up and see if the latency goes down. But are there any questions? Question over there.
Thank you for the talk. We are in the process of also setting up Thanos, and there's one thing that we have noticed is we are using GCS, and if we query if we query the long storage, basically all of our requests times out. Have you also experienced such issues when you have implemented this, and if so, how did you solve this?
I can use this mic. So you want to make sure that you set up the compactor, because essentially what the compactor does is it's the thing that's responsible for downsampling. So I mentioned that the blocks are immutable, right? And this is kind of where it's not a lie, but what the compactor does is multiple things. It takes smaller blocks and produces larger blocks out of those, but at the same time it performs downsampling. So it rolls up the values to a 5-minute rollup and an hour rollup and so on. And then the Thanos querier, when you do a query over a really long time span, it can automatically detect the optimal resolution for this particular query. And then instead of querying a resolution of 15 seconds, when you're querying over a year, you don't actually need that resolution, right? You can't even place the dots in your Grafana graph for that. So instead, it would use the 1-hour resolution. So I highly recommend checking that out if you haven't already. And if that still doesn't work, then open an issue for us, and we'll look into it. Other questions right over there.
Hi guys, thanks for the talk. I have also a short question. We have customers which are collecting per day metrics in a size of 2-3 terabytes. And I saw Thanos is storing all the metrics on object store. How does it fit in terms of performance? I mean, our customers are trying to push all these metrics currently to Hadoop with Spark or something like that to train models to analyze all the metrics. And does it fit also with Thanos in this scale?
Yeah, so Thanos has multiple layers of caches. So it doesn't necessarily always go to object storage directly. So basically, when the store API starts, it downloads the index so that it basically you can think of it as an mmap, but instead of against your local disk, against object storage. And so it will kind of fetch only the data that it needs and has an additional cache on disk. So kind of the recommendation is that for that local on-disk cache, you should probably use SSDs, and then you get pretty much the same performance. We're here.
I was just going to ask about scaling of the actual setup apart from your test app. So obviously across different cloud providers, makes sense that you have like the query API or the querier part of it there available to do the store API. If you're on a single cloud provider and you wanted to scale out Thanos itself, does it make sense putting that extra layer of the querier between queriers, or would it be scaling out store instead?
So I guess that's a little bit my own opinion. I think you should probably try out a couple of things, but I don't think you would need the additional layer of the querier. That's usually meant to like work with your topology, and you don't actually have that problem. So I'd recommend just using the sidecars or the receive to do the hot querying, and then upload to object storage and do the long-term data there. Maybe you want to do multiple queries across availability zones or something like that, but that would be for availability and not so much performance. Over here, but I think there was also someone in the back who has been raising their hand for a while. But no.
Yeah, I have one question around this new proposal, Thanos receiver. The thing is that we use, for example, only Thanos sidecar and querier without long-term storage. So with this new proposal, does it mean that Thanos sidecar will be deprecated?
No, so these are, there is a place for both of these. Remote write also has some overhead. It has different characteristics. So these both are here to stay, if that answers the question.
Thanks for the talk, both of you. We are already using Linkerd 1 for some of the legacy infrastructure we have. We are looking forward for using service mesh in our new infrastructure. We didn't decide yet what. Can you give me what, like right now, most people talk about Istio Envoy or Linkerd 2. Can you give me what the point that you think, in your opinion, the best for Linkerd to go to, or what is the point that is missing from Linkerd and then go to Istio? And thanks for being honest.
Sure. Yeah, that's a question we get a lot. Yeah, you probably hear quite a bit about Istio, and Linkerd and Istio are kind of two of the main service meshes in the space. I'd say 2 areas where we're doing pretty well, and 1 area that we need a little catch up on. I think with Linkerd, we really focus on usability and being really clear to the operator on what's going on. So you saw like in this demo, I did like a full installation of Linkerd and then like layered in an application, and that all took like a few seconds to minutes. That's one of our like primary design goals. We want it to be as simple as possible. And with more time, there's a bunch of debugging tools that we build into Linkerd because we want it to be very transparent. It's a really critical part of your infrastructure, and so we want to be really clear on like what's going on and kind of what's the state of all the different components. So that's one, like usability. The other is performance. There are some like sort of controversial blog posts right now if you Google for Istio Linkerd benchmarking. But overall, I think we've done pretty well there. Rust was a bit of a bet a year and a half ago, but I think it's paying off for us. The area that I think we need to play catch up is we don't quite have the features. We don't quite yet have traffic shifting like Canary and blue-green deploys. We're planning that in the next month or 2, but because Linkerd 2 was a from-the-ground-up rewrite like a year ago, we have more features to implement. As you probably know, like Linkerd 1 is like very full-featured, but that was thanks to like 10 years of development at Twitter. So we're kind of like re-implementing a lot of that logic in Rust and Go now.
Do I get any tracing with Linkerd?
Oh, that's a good question. So the question was, do you get tracing with Linkerd? So like, explicit tracing like Zipkin or open tracing, we do not provide that. You would have to add it yourself. Our thinking is that with Linkerd, because it's managing traffic between all of the microservices in your cluster, we can show you every edge in your topology graph, and we can give you success rate, latency, and request rate on every edge. So we can't follow a single request all the way through your system, but we can pinpoint where on the graph an edge is failing, and that lets you like zero in on the requests that are specifically there, which we found that in a majority of debugging cases, like that's what you really need. You need to know which request is failing where, and not necessarily to follow an entire lifetime of a request. Sure.
I don't think we have time for any more questions on the stage, so thank you again for the talk.
Thank you. Good job, dude.